So now let's look at doing some triple integrals over more general solids. So let's just sort of sketch out a solid here in 3 dimensions. For example, you could have a solid which, say, is bounded by sort of a bowl shape on bottom here and kind of capped off at the top. So let's say this is my solid D. And we'd like to know, how do you set up a triple integral over a region like this? Well, the idea here is that my solid has kind of a bottom surface and a top surface. So the bottom surface you might write as something like, say, z equals g of x, y. And then the top surface you might write as z equals h of x, y. And then there's kind of a shadow of this whole thing in the xy plane. So I have some region down here that I'll call S for shadow. And so the idea then, basically, if I kind of slice through this using what you might call z-rays, sort of vertical lines that are parallel to the z-axis, every z-ray will enter the solid along this first curve, first surface, z equals g of xy, and they'll all leave on the second surface, z equals h of xy. And then S shows all of the places that I need to use z-rays. And it turns out that then what you can do, for the inside integral, you're going to use bounds of g of xy to h of xy. So here we have the same function on the inside as before. I'm using z first. So that's what the inside integral looks like. And then what about the other two? Well, sort of what you're going to do is, once you set up the inside integral, you just set up the outside integral as if you were trying to integrate over that shadow S. So you just kind of zoom in on whatever S is, and then you set it up in whatever way makes sense. For example, if you want to slice it in the y direction, then you want some bottom curve and some top curve, and you set it up like that. So it really relies on you being able to set up double integrals very well, in addition to adding kind of a new complication to things. Well, let me just show you kind of a concrete example. So let's suppose that we want to, let's just set up an integral of the function f of x, y, z over the solid that is bounded by the plane, say, 3x plus 2y plus 4z equals 12. And then the coordinate planes, the planes x equals 0, y equals 0, and z equals 0. Well, let's first of all sketch this plane out, the 3x plus 2y plus 4z equals 12. One good way to get a bit of a handle on a plane is to find any 3 points on that plane, and then draw the triangle that connects those 3 points, and that triangle has to be part of your plane. And a nice way to find 3 points is to just find the intercepts of your plane with the x and y and z axes. So remember, if you want the z-intercept, that means you want x equals 0 and y equals 0. And when x and y are both 0, well, then z has to be 3 in order to satisfy this equation. And I'm not going to fuss on the scale too much here. I'll just kind of label the points. So the z-intercept is 3, the y-intercept is going to be 6, and the x-intercept is going to be 4. And again, I just found those by, in each case, setting two of the variables equal to 0 and finding the value of the third one. Well, that means that this triangle that kind of connects those 3 points, that triangle is part of the plane here. So I have a plane that's kind of slanting down, like as the z value decreases, the x and the y values are increasing. Now the solid that we're looking at then is in fact this tetrahedron, this kind of pyramid over a triangle. And it has 4 triangular faces. One is a triangle that I drew, but in drawing that triangle I kind of accidentally made 3 more triangles. For example, there's this one triangle that goes from z equals 3 down to the origin, over to y equals 6, and then back up here. And then there's a triangle in the xy plane and a triangle in the xz plane. So that's the solid that we're looking at. So first what we want to do is try to identify what is the top surface and what is the bottom surface, which is to say we're trying to figure out basically what the range of z values is. And in this case the solid rests on the xy plane, so the bottom z value is really just 0. And if you imagine a line that is parallel to the z-axis going through this solid, it starts here in the xy plane, and what will happen is that it will leave my solid somewhere on this slanted triangle that was bounded by this plane here. So really, the top surface is given by that plane, so I just have to solve that plane equation for z, which is not real pretty. It's 12 minus 3x minus 2y all divided by 4. But that's fine, that's just what the upper surface is. So these will form the bounds of the inside integral, the bounds of z. Next thing to do is to look at what the shadow is. So the shadow is something in the xy plane. And in this case, the shadow really is just the widest part of this solid, and it's actually sitting here in the xy plane. It goes up to y equals 6 and down to y equals 4. So the shadow is this kind of triangle here. And if you want to slice that, well, let's slice it vertically. So I want a range of y values. And then the last one is going to be the range of x values, which will be just numeric. It's clear from the picture that the range of y values starts at y equals 0, and then it leaves on this line right here. Well, that line is the intersection of this plane from before with the xy plane, which is to say that I just set z equal to 0. That's what the xy plane is. So that's the line 3x plus 2y is equal to 12. And if you solve that for y, you get that y is 12 minus 3x all over 2. And finally, the range of x values. Where do I need to actually do these vertical slices? Well, from 0 to 4. And so finally, that means that our integral will be the integral from 0 to 4 of the integral from 0 to 12 minus 3x over 2 of the integral from 0 to 12 minus 3x minus 2y all over 4 of whatever my function is. And again, that's dz, dy, dx. Okay, so that's the basic idea. You have to identify a top surface and a bottom surface so that you can find the z-bounds. Then you have to find what the shadow is, and then you just set up the integral for the shadow the same way as you've already been doing for double integrals.